Good morning, good afternoon, and good evening to everyone who has joined us from across Australia and around the world. I'm Tom Keegan from Matrix, Australia's residential research institute for the mathematical sciences. A very special welcome to our guest presenter today, Dr. Yilin Wang from MIT Mathematics, who will present the topic, How Round is a Jordan Curve? Yilin is CLE Moore Instructor at MIT, a position she has held since 2019. It follows having obtained her PhD advised by Welding and Kahler at ETH Zurich. Yilin is currently participating in the program The Analysis and Geometry of Random Shapes at MSRI Berkeley in California. After that, Yilin will take up a new position in France as a junior professor. If during the talk you have a question, please register it via the Q&A function rather than chat. At the end, I'll enable you to ask your question via your microphone. And if you'd like to switch on your camera via Zoom too, you're most welcome to do that. If you would like closed captions enabled on Zoom, send me a message via chat and I can make this available to you. Yilin, thank you very much for joining us today. It's a real pleasure to have you, and we look forward to you sharing your knowledge and insights into this very important topic. Thank you.
Thanks a lot for the invitation and the introduction. Let me just share my screen. Can you see it now?
Yes, that's very nice.
Right, okay. So I'm very happy to speak here, and I hope I could visit the Matrix in person, but hope I will have a chance next time. So today I will talk about a topic about in connection to probability theory and more classical complex analysis, and it will touch on a few different subjects, and I hope that will be interesting for all of you. So as a reference, will be a lot of paper involved. So I think the best reference is this survey paper, which is just published in probability surveys. And let me just start with the Mobius transformations. So we consider the Riemann sphere, which is just a complex plane where I add infinity to it. It's a Riemann surface. And it has the group of conformal transformations, which is represented by this PSL2C group. These are just acting on the sphere by these fractional linear transformations. And these are also called Mobius transformations. And one particular feature about it is that it will send circles to circles. And when I say how round the Jordan curve is, I will have in mind about some energy which measures the roundness and which has to be invariant under this PSL2C action. And in particular, it has to be also zero if and only if gamma is a circle. And this Loewner energy will be this quantity. It was motivated by some probabilistic theory like SLE, in particular, is large deviations. So here you see SLE 0 plus, it actually means that SLE has a parameter kappa, and the large deviation is describing some kappa goes to zero asymptotic behavior of these random curves. And intuitively speaking, is measuring how likely this SLE's kappa when kappa goes to zero, and this asymptotics, how likely it is to be close to a given curve gamma. I give it deterministic curve gamma associated to a number called Loewner energy, which is greater or equal to zero. And this Loewner energy is further connected to this class of Weil-Petersson quasi-circles as a class of Jordan curves has been studied by many people, and I will discuss about that later. And to give you the quick definition is that we will use something called Loewner evolution. The Loewner evolution is first we can consider a chord, which just means that in a simply connected domain and with two boundary points, a chord is a simple path connecting the two boundary points. And later on, for the Jordan curve, it will be a limit when from this chordal setup. And if you have, so everything would be conformal invariant. So if you have another simply connected domain, I will just take a conformal map, sending it to the upper half plane. A conformal map, I just mean a biholomorphic function. And you have a simple chord in the upper half plane connecting 0 to infinity. There is something called Loewner's transform, which will encode this simple curve gamma into a real value driving function. And vice versa, if I start with the driving function, I can recover this curve gamma using the Loewner equation. And more precisely, if one consider this Jordan curve gamma, and you look at you cut out the first bit of this curve gamma, the complement of this red curve here is a simply connected domain. And using Riemann mapping theorem, I can map this yellow area to the upper half plane while fixing infinity. I can choose some normalization so that this conformal map is like identity plus some terms which goes to 0 as z goes to infinity. So once I choose this normalization, this conformal map is uniquely determined. And this number here, this coefficient here, it would be a positive number, which is called the capacity of the red piece. It's a half plane capacity. And if I'm given this curve gamma, for each initial bit, I can see what is the capacity of it, and I will choose a special parameterization of the gamma such that this number here is exactly 2t. And then I call this map, conformal map, GT. And the tip here, you see that this conformal map will send the two sides of this red piece of curve to the real line. So it will open up to two sides of this tip. And the image of the tip is somewhere on the real line, and this is what I call WT. This is the image of GT of gamma T. So gamma is now capacity parameterized. And W is called the driving function of gamma. And we have that W0 equals 0, then the map is the identity map. And if we look at the GT as a function of t, then it will satisfy this differential equation with a starting initial condition G naught of z equals to z. And it also has the property of the following. If I look at this orange curve that's under the image of, so here if I stop at the time s, the image of GS of gamma, the future of the gamma, if this orange curve, its driving function is simply the increment of the original driving function. And if I scale my curve gamma by a positive number c, then the driving function changes in this very explicit way. So these two transformations, it's true for any simple curve, it will satisfy this property. But if one asks what curve there will be invariant under these two transformations, basically there's just one function, but it will be less. That will be a bit less interesting. But if we consider random driving function, like this square root of kappa times the Brownian motion, then the Brownian motion will be invariant under these two transformations. And if we look at the curve generated by square root kappa times b, it will be the standard Brownian motion. It will be called SLE. And when kappa equals 0, this is a deterministic case. And this looks like an uninteresting case, which is just a curve going up, straight up. But actually, it will turn out to be one of the most important example of this Loewner transform. So here, I'm just say a bit about SLE. So there's actually a phase transition depending on this kappa. When kappa is between 0 and 4, it's almost surely a simple curve. When kappa between 4 and 8, the conformal map will be defined also inside this outside of this orange set, but this growing family of orange set, it can be still described by a self-touching curve. And when kappa is greater than 8, it's almost surely a space-filling curve. And because of Brownian motion itself has a lot of universality property, like its scaling limits of all kinds of simple random walk, so this universality property, after you plug in that to the Loewner transform, this is what I call the Loewner transform, it makes this SLE kappa to be very universal. Actually, it was introduced to describe scaling limits of interfaces, and now it's also proved to be a mini scaling limit of interfaces into these statistical mechanics models. For instance, for different values of kappa, different kappa correspond to different models. And like this one, for kappa equals 1/3, it should be the scaling limit of self-avoiding walk, and this is conjectural, and all the rest have been proved. The Loewner energy is just defined to be the Dirichlet energy of the driving function. If I start, I can even define the Loewner energy for a chord, which is connecting two boundary points of another simply connected domain D. I just use this conformal map, sending the domain D to the upper half plane. Now I can write down its driving function, and I take the Dirichlet energy of this driving function. Well, the Dirichlet energy might not be always defined. If it's, say, if it's not even not absolute continuous, you cannot write down what is W prime. But in this case, we just take the Dirichlet energy to be infinity. So this Loewner energy is well defined for any curve in the upper half plane, but actually also well defined for this curve in D. Here, actually, the phi conformal map, if sending the boundary point to boundary point, is uniquely defined up to a scaling. But however, we can check that because of this transformation rule of the driving function, the new driving function under scaling would look like this. It actually has the same Dirichlet energy. That's why the Loewner energy of gamma is well defined in any simply connected domain. And that's also the other reason for why SLE is also well defined in the domain DAB, because Brownian motion is invariant under this transformation. But this is definition. What's the relation to SLE? So this is the Schroeder theorem, which relates the Dirichlet energy to Brownian motion. It's about the large deviation. And heuristically, it means that if I take a very small kappa, this multiple of square root kappa times b being close to a driving function, given function w, this probability should decay very fast to 0 when kappa goes to 0, unless the energy itself, Dirichlet energy itself, is 0, which is given by the 0 function. But if my driving function w has a finite Dirichlet energy, then this probability is decaying like exponential minus Dirichlet energy over kappa. And if we just translate that to the SLE language naively, okay, this Brownian motion becomes SLE kappa, but the probability of SLE kappa being close to a given curve gamma decays exponentially, like exponential minus this Loewner energy of gamma divided by kappa. And here, what this being close means, what has been proved in this work jointly with Peterson, is that for the Hausdorff distance in the unit disk, and this is what is the large deviation, but it is believed that is for other finer topology, this result should also hold. Right, but however, Actually, this is a non-trivial result going from Schroeder theorem to this Hausdorff distance large deviation, just because that the transformation from the driving function to the curve itself is highly non-continuous. If it was continuous, one can obtain this result easily. But however, this Schroeder theorem is still behind this SLE result. One can therefore think about what is the Loewner energy of this blue curve. It's measuring how likely SLE kappa want to stay around this curve gamma. So when the Loewner energy is 0, that would correspond to, in this picture, this dashed line, which is the 0 driving function. And in the previous domain, this dashed line is the pre-image of this vertical line, and that is called hyperbolic geodesic between A and B, which we can take as as definition of hyperbolic geodesic. All right, finally, let me come to the loop energy. Now, if I have a Jordan curve and say it's oriented in this direction, and I take a point on it and call it the root of my Jordan curve, I define the loop energy rooted at gamma naught to be this limit. I take another point on the curve and this green part, and view this curve being on the Riemann sphere. The complement of this green part is a simply connected domain. And now this orange curve is a curve connecting two boundary points of the simply connected domain. And therefore, I can write down its caudal Loewner energy. All right, let me recall that how you should do. You should map the complement of the green piece and to the complement to the upper half plane. You get the curve, orange curve from 0 to infinity. You write down its driving function, take its Dirichlet energy. You get this caudal Loewner energy. And then the loop energy is obtained by taking the epsilon goes to 0. You shrink this green part towards its root. This limit exists. In fact, when epsilon goes to 0, this is always increasing. It could be infinity, but let me just take that. If it's infinity, it's infinity. But this loop energy has been introduced in a joint work with Stefan Roeder. And we prove that this energy actually doesn't depend on this root and also doesn't depend on the orientation of the curve. So therefore, this loop energy is in fact better viewed as an energy on this Jordan curve. And furthermore, we can show that the energy is 0 if and only if gamma is a circle. Phi, if you have a Mobius transformation, then the Loewner energy of the image has to be itself, because this caudal energy is defined using conformal maps. And we can also show that the Loewner energy is finite, then gamma is a rectifiable quasi-circle. Not all quasi-circle are rectifiable. So this is a very small class of quasi-circle. And in fact, if one think about why there's so many symmetries, it's actually quite surprising to see that this root and this loop energy doesn't depend on the root, because it seems that if you want to write down the driving function, it's very much depending on how you parameterize the curve, especially where it starts. But now I see. Can you see the slides with two questions? Yeah.
Oh, no, we can't see those, Yilin.
Yes, I also get, maybe even try to stop share.
Yep.
I'll share again. Yeah.
Yep, that's good.
It works. Okay. So we wonder why there are so many symmetries, and the symmetry coming from, say, changing the orientation or reroute the curve. And the other question was very natural. So what are the curves with finite energy? Try to answer this question, we will actually have to change the viewpoint. I hope that will be also inspiring. That if you have a Jordan curve, see this gamma, I can look at welding homomorphism, and that means that one consider the conformal map from the unit disk to inside of the curve gamma, and another conformal map G from outside of the unit disk to outside of the curve. These two functions f and g, they will extend to a homomorphism of the closure of the domain of definition, because this gamma is a Jordan curve and this is a Carrot-Teradori theorem, which says that you can extend this conformal map to a homomorphism of the closure. Then f and g, both of them will give you a homomorphism from the circle to the curve gamma. Say this point here is mapped to a point on gamma by f. And when you go back with G, like G inverse, it will send this point to some other point on the circle. And this map phi is from this point to this point, is a homomorphism from the circle. And we have seen that the Loewner energy is finite, then gamma is a quasi-circle, which you can take this as definition being saying that the welding homomorphism is quasi-symmetric. And quasi-symmetric just means that if you take any 3 points on the circle, like with equidistant, then in the image, their distance, the ratio of their distance is bounded above and below from by the same number. So that says that there is some, one can characterize some properties of the curve using their welding homomorphisms. However, we also saw that not all quasi-circles has finite Loewner energy. So this is a new diagram. And if one look at the space of the quasi-symmetric homomorphism of the circle is a group, and the Mobius transformation of the circle, that's just all the Mobius transformation which preserves as a whole set the circle or the unit disk. And this quotient of the quasi-symmetric group by the Mobius transformation of the circle, which of course preserves the circle, this is called the universal Teichmueller space. And on the right-hand side, I write down what are the curves which is corresponding to the this welding. And this quotient called the universal Teichmueller space is because the other Teichmueller space of compact surfaces, they embed holomorphically into this space. There's some complex structure on this infinite-dimensional space that not get into detail. But there's also a very nice subgroup, which is all the diffeomorphism of the circle, C infinity smooth diffeomorphism, and they correspond to smooth curves. This is a very small subclass. And string theorists already in the 80s, like in Bovik-Rajiv and later Nakviovsky, and they have been looking at some Kahler structure on this space, and also Witten, that it says that there is a very natural complex structure for which there's a unique homogeneous Kahler metric. And this Kahler metric is called Weil-Petersson metric. And actually this Kahler metric, if you give you a very few, it's unique, essentially unique just up to a scaling factor. And being Kahler, it just means that it's a three compatible structure, a Riemannian metric, a symplectic form, and also the complex structure. So, but however, this space of the smooth curve, this smooth part of this Teichmueller space is not closed, it's not complete. And for this Weil-Petersson metric, and the intermediate space, which has been made rigorous by Taktajan and this seminal work on this intermediate space, we call the Weil-Petersson Teichmueller space, and they denote it as a G01. And those welding corresponds to the curve called Weil-Petersson quasicircles. And Dr. Dantel also showed that this is an infinite dimensional Kähler-Einstein manifold, which means that if one compute the Ricci curvature for this Weil-Petersson metric, which inside the Ricci you have to take infinite sum in the trace, which without any normalization, this sum is summable. And this Ricci curvature is proportional to the Riemann metric. And this is quite amazing. It's a space with a lot of structure and all the good properties. And more importantly, they introduced this number called the universal Liouville action, which is only defined for this intermediate space or just for Weil-Petersson quasicircles. It's very simple. You just look at these two conformal maps and write them just explicit in terms of F and G. And they show that this quantity is a Kähler potential for the Weil-Petersson metric. And which just means that if one can take dd bar of this function, you can recover the symplectic form there. Here one can just, I'm just presenting this to say that there is a certain structure on this intermediate space coming from this unique Kähler metric on the smooth part. And moreover, this Kähler potential is just a scalar function, a very simple expression, which captures all the information about the metric. And moreover, this quantity is only defined for the intermediate space for Weil-Petersson quasicircle. All right, and the main result that obtained is that this Loewner energy, which comes from this large deviation of SLE when taking the limit when going to the root of for a Jordan curve, this Loewner energy is finite if and only if gamma is a Weil-Petersson quasicircle, and moreover, this Loewner energy is proportional to this Kähler potential. So on the right-hand side, here it's a very simple expression using F and G. Here, there's clearly no root. Therefore, the root independence is very clear. Whereas on the left-hand side, from definition, it's kind of a miracle why it doesn't depend on the root. But however, the definition from the Loewner energy, it uses Loewner chain, where kind of you explore the curve little by little. You make it into a process which further connects to the probability theory of SLE. So both definition has its strength. So this identity is kind of building this bridge between the probability theory of SLE to this class of Weil-Petersson quasicircle. And the deep reason behind it is still quite obscure to me, that why there's such a coincidence. Is that the coincidence, or there's deep reason behind that the probability theory of SLE is closely related to this Kähler geometry of this infinite dimensional space of Jordan curves. But however, I cannot answer this question. But however, I will show you some examples of how we explore this link in order to obtain some new results about Weil-Petersson quasicircles. But before that, let me give you a bit more of his history. So I already said it's motivated by string theory, where they studied Kähler geometry on the smooth part. But more recently, in the 21st century, switched to studying the geometric analytic perspectives of those curves or these weldings. And many works has been done by Cui and Shen, Tang, and Wu and their collaborators. Also, Dr. Dantel mentioned, and also recent work by Chris Bishop, which gives a lot of more geometric characterization of these curves. And Ratner, Schipper, Staubach, they propose that in order to make sense of the Ziegel conformal field theory, one need to use homomorphism, Weil-Petersson homomorphisms in order to glue surfaces together. So this is a very essential building block in their conformal field theory. Also, because there's this such nice metric which has a actually negative curvature of the Weil-Petersson metric, and so it's kind of nice to to describe the distance of two different shapes, and this is the approach taken by Schramm and Mumford to apply to computer vision, and their relation to KdV equations. And also in the work by Chris Bishop, he's established some holographic principles of objects in hyperbolic 3 space. And my work is related more in connection with random conformal geometry, which relates to SLE, Gaussian free field, and all that circles of questions. Let me also give you a few examples about these definitions of equivalent definitions of Weil-Petersson quasi-circle. And there's currently a huge numbers of equivalent description, which looks very different, but they describe the same class of curves. And for instance, this one is that when gamma is Weil-Petersson if and only if the Schwarzian derivative is L2 integrable with respect to inverse of hyperbolic metric. And Schwarzian derivative is a third degree derivative, which vanishes all the Mobius transformations. So if you have a Mobius transformation, then gamma has to be a circle, and this Schwarzian is just 0. So this energy, this term, by the way, this term is not equal to the Loewner energy, but if it's finite, then the Loewner energy is finite, if and only if it's finite. And Bishop, for instance, shows this one that because all the Mobius transformation, the PSL2C group is also the isometry of hyperbolic 3 space. The hyperbolic 3 space is just a half space where the metric is proportional to the Euclidean one, but divided by the height squared. And all the isometry of H3, their boundary value is on the Riemann sphere and just given by the Mobius transformations. And he shows that gamma is Weil-Petersson if and only if you can find the minimal surface in the hyperbolic 3 space with boundary this gamma with finite total curvature. So the area of this surface sigma is of course infinite because it's getting close to the boundary. But however, the curvature, the principal curvature here is a minimal surface means that the principal curvature sum up to 0. So you take the k squared integrated against the area form, it's actually finite. It's also a nice result. And this result due to Teichmueller and Till, and also actually you should mention that the Shen has a similar result, that if gamma is Weil-Petersson, if and only if, that the Gronsky operator is some operator associated to a curve gamma is Hilbert-Schmidt. And moreover, this Loewner energy can be, in fact, expressed in terms of the determinant of identity minus B star B. This is a self-adjoint operator. You can take some determinant of that and take a log of it. You get the Loewner energy. And then give you the definition of Gronsky operator based on a classical object in geometric function theory. And more recently, a result by Kurt Johansson shows that it's some relation to Coulomb gas as well, that Zn is the partition function of Coulomb gas on gamma, with the n being the number of particles. And this partition function actually blows up when n goes to infinity, like a 2 pi to the power n, and look times capacity to the power n squared. But if you divide by this leading term, then take n goes to infinity, this actually equals the exponential of the Loewner energy divided by 24. Again, this is finite if and only if this gamma is Weil-Petersson. And their proof is based on the relation to the Gronsky operator. It's closer to the last one. We can see that this Weil-Petersson quasicircle, together with the one using the Loewner energy, is really having a very different but equivalent description about them. So let me just give you one example. I cannot say too much about how one can use this link between SLE and Weil-Petersson quasicircles to give you more results about Weil-Petersson quasicircles. I just remind you that when I take the kappa goes to 0, large deviation, I obtain the Loewner energy, which measures how likely that SLE kappa to stay close to a given curve gamma. And that's the Loewner energy equals to this S1, the Liouville action divided by pi. And in the SLE literature, there's a result called SLE duality, which says that if you take SLE kappa for very large kappa, then the boundary for large kappa is almost surely a space-fitting curve. Then the boundary of this curve will be a SLE 16 over kappa curve. So for very large kappa,
I'm still not sure about that.
Oh, my Siri is speaking. Oh, sorry about that. So one can expect that if I have large deviation result for a small kappa, it should be related to some large kappa large deviation. In fact, we obtain a result, but we study the large deviation of SLE 16 over kappa when kappa goes to, so here kappa goes to 0, the ratio goes to infinity, in a joint work with Maurice An and Ming J. Park. And the large deviation rate function, they are called the Loewner-Kufarev energy. And in a work with Friedrich Wickland, we established the link between the Loewner energy and the Loewner-Kufarev energy. Let me just give you the statement. But so here one need to think about what happened when kappa goes to infinity. So when kappa goes to infinity, because this curve grows very quickly from everywhere, so in the end we'll get evolution of domains, which not anymore growing from the tip, but it will grow from everywhere. So for that we need an object called the Loewner-Kufarev equation, therefore the name, which is describing the whole family of the conformal maps. If you have a shrinking family of simply connected domain, so if we assume this conformal radius, they're all like decreasing like exponential minus t. You look at this conformal map ft from unit disk to each of the domains such that it fixes 0 and its derivative being exponential minus t. Then this family of conformal map ft will satisfy the following equation. Its time derivative is expressed as minus z times the spatial derivative of ft, but multiplied by a holomorphic function here. And this function has positive real part, and it can be represented by this called Hergloss integral. This is rho t is the probability measure on the circle. And it's not very important how this equation really look like. What one should remember is that if you have a shrinking family of simply connected domain, then you can describe this by a family of probability measure on the circle. So this is, you can look at all the only requirement in rho t, the dependence in t is just measurable. And can think this correspondence between the family of driving measure, rho t, it give you a family of conformal map ft, or this is evolution family of simply connected domain. For instance, if you take the driving measure to be a uniform measure, then it will grow everywhere uniformly. You will just get this concentric disk centered at 0. And if rho t is constant in t, then we're now inside this case where the conformal maps will become a semi-group, ft plus s equals ft composed with fs. If rho t is a Dirac measure, a time-dependent Dirac measure, then you will get the case where it's the classical Loewner equation, and when kappa between 4, if we take the driving function to be a Brownian motion on the circle, then we will also have the same phase transitions. You get fractal curve starting from infinity towards 0, or self-touching curve and curve or kappa larger than 8, your space filling curve going towards 0. So this is the Lovener equation, which is slightly different than the one I presented at the beginning. That one is targeting at the boundary point, and here there's everything is targeting at 0 and coming from infinity. So the fundamental question about this Lovener-Kufarev equation is that how can one relate the geometry of this family of domains to the properties of the driving measures? There are sufficient conditions to generate quasi-circles, but not necessary condition that was known. But however, because inspired by results from random conformal geometry, we can give you some complete characterization for Weil-Petersson quasi-circles. So this one is our result. If S of rho, I will give you the definition of that in the next slide, but this is an energy which is coming from the large kappa, large deviation of a SLE. If this S of rho is finite, then all the boundary of the dt is a Weil-Petersson quasi-circle with no exception. And moreover, the Lovener energy of this boundary is less or equal to 16 times of the Lovener-Kufarev energy of the curve generating it. And the union of these curves, that covers the whole plane. And the last thing is that it's continuous in time t for the parameterization by conformal map. And this is what we call a foliation by Weil-Petersson quasicircle. It's really covering the whole sphere. And this is the Lovener-Kufarev energy. So for a measure rho, which will given by the family of actually probability measure rho t, where t goes from -infinity to infinity, S of rho is just the integral of a quantity of L of rho t, where L of rho t is the Dirichlet energy of the square root of the density of the rho t. So this is the energy which comes from the large deviation of large kappa SLE, and more precisely actually from the occupation measure of Brownian motion on the circle. So here, why this result is relevant to the large deviation of SLE. Here I'm saying that if we compare this to the SLE duality result, it's saying that for large kappa, the domain you get, this boundary corresponds to small kappa. And here we're saying the same thing. If we look at the rate function for a large kappa SLE, then the boundary of the domain you obtain has finite energy for the small kappa large deviation rate function. The Weil-Petersson quasicircle, and the Lovener energy itself corresponds to the SLE 0 plus large deviation. So if one has SLE GFF, SLE random conformal geometry in mind, this result is what one should expect to have. But however, the proof of is totally deterministic. And moreover, actually, we can also show that if I have any Weil-Petersson quasicircle, then I can find a measure rho which generates this curve as a leaf. So this is really saying that all the Weil-Petersson quasicircle they can obtain by some measure which is finite Lovener-Kufarev energy, and all the leaves obtained by this Lovener-Kufarev energy curve are Weil-Petersson quasicircle. Well, I won't go into the proof. This is the final result. It's saying that we can actually even give you a more quantitative description of this Lovener-Kufarev energy by describing this winding function. So if you have a foliation by Weil-Petersson quasicircle, one can look at what is the angle between each tangent with the circle center at 0. This tells you how much is deviate from the case where all the leaves are concentric disks, concentric circles. And phi gives you a function defined almost everywhere on the plane. And this Lovener-Kufarev energy is in fact equal to the Dirichlet energy of this winding function. And this is actually how we prove that each curve is a Weil-Petersson quasicircle. So this is the final slide, and there's another part of the story actually relates the Dirichlet energy of functions living on the whole plane to some large deviation of a Gaussian free field. And because of small kappa SLE gives you the Loewner energy, large kappa SLE give you Loewner-Kufarev energy. There's a duality between them. There's a connection to Gaussian free field. So we guessed and proved that on the right-hand side, you have a similar story. Like here, you have a foliation by Weil-Petersson quasicircle, and their relation between these two energies are called energy duality. And the way we prove it is also going through some Dirichlet energy also in between. Yeah, so I hope that's give you an overview about this. It's a very beautiful subject about the Weil-Petersson quasicircle. There's still a lot of things to be understood, but now we have this new world open to random conformal geometry. We hope that there will be a more exciting development by using results from one side to the other side. Okay, so thanks for your attention, and happy to answer questions.
Oh, thanks very much, Yilin, for a very interesting talk. Now, if you would like to lodge questions via the Q&A feature, please do so. We can read them out on your behalf if you like, but if you would like to ask in person, we can also enable your camera and microphone. Yilin, I'll ask a couple of generic questions. You're currently involved in the analysis and geometry and random shapes program at MSRI. Are you able to tell us a little bit about what you're hoping to achieve from the program and what your experience is like there in California?
Oh, definitely. Yeah, I'm giving a talk. I'm also speaking from the office now. So for the program, it has been really amazing so far. Especially you have many people who had shared a very common interest, but from very different background as well. And for instance, when we just arrived, work with I discussed a lot with say Masha Godzina from Connecticut. And she works on infinite dimensional Brownian motion, the Brownian motion on infinite dimensional space, especially the group of the diffeomorphisms of the circle. This is an example of an infinite dimensional space. And we have very, very different background. But however, both of us are interested in understanding the random measure, the measures, natural measures on the group of diffeomorphism of the circle. And over there's a SLE, these are curves. On infinite dimensional space, and having a Brownian motion there, it's there should be connected in some way. So, but since our background are very different, we start reading group together, and we start with 3 people, and then many people get interested, and it becomes a reading group of 20, 30 people, and we just try to share what we know and try to understand things. It has been generated a lot of questions, and I've learned a lot here. And so that's one thing that I've been also working on with Masha, and every day just have so many people we can talk to and to discuss new project, and having a question, like you have a quick question before you have to write an email waiting for a week and then before getting an answer. Now you just go next door and knock at the door. It's really amazing that also after 3 years of pandemic, 2 years in pandemic, haven't seen people
much more efficient and engaging, isn't it?
Yeah. Oh,
terrific. We have a question. Sorry, I don't know your name, Thermotronica, so I'll ask the question in person. Galfon's constant applicable question mark.
You can say a bit more specifically the question.
If you give your name also, we can enable you to ask the question in person if you like. So I'll just enable Hugo to ask his question in person. There we go, Hugo. If you enable your mic and camera, you can ask away. I'll try that again. Any luck, Hugo? Yep, here we go. Okay, if you turn your mic on and camera, you can ask.
Oh, thanks for bearing with me there. Very nice talk. Thank you very much. What I meant with the Gelfand's constant is I noticed you you brought up in the Kahler manifold part, I believe there was something about Gaussian free field.
Yes.
So I was just kind of throwing it out there if with the time dependent Dirac measure, I was thinking about the split Arctonians, and I was just wondering if instead of using the manifold to be let me use pi and phi over here. Sorry, I'm all over the place. But just that power move, would that influence the curvature in any way, just taking it to the power?
By power, which power that you mean? Like
so like e to the pi, instead of where you wrote, let's see, I guess it would be, sorry, I come from algebraic topology mostly. So in PSL 2C,
yeah,
if you were to, when you're calculating the chords and then the probabilistic function, since you're using the Gaussian curvature to see the volume, would going to the powers affect it in any way?
Oh, you mean like this one?
Yeah, right here.
This is a very good question. Actually, so there are many things where so here all the way Peterson, they're like L2 theory, more or less. Like for instance, here, like you see L2 power of the Schwarzian.
Yes.
And there's many, actually there's other, it's basically the L2 theory. Like in the driving function is also Dirichlet energy is the L2 theory. There are many things we can to make into LP with P different than 2. But for this one, I don't think it's known, like for what is if you change this 2 to some other P, whether it's well, definitely you can define it to look at what are the curves for which k to the power P, this integral is finite. I don't think it's known, but here there is this.
Yeah, this was super interesting.
This will be P. This will be and this power would have to change a bit as well. But there's a natural choice to generalize to this called the P-Schatten class.
Oh, you can. Okay.
Yeah. So and also the P-Schatten class is also. This is also L2 theory of the Gronsky operator. This can be also made to power P. So this is the singular, the spectrum singular to the square singular values to the power 2, and but you can change that to power P as well. So these two are equivalent. The P-Schatten class, there's a characterization in LP of the Gronsky operator, and in the Schwarzian, and also in the Beltrami coefficient, which I didn't write down. So
Perfect,
a reference for it is Gavin Jones, which yeah, right.
Thanks for interpreting my question. I kind of don't know what I mean when I'm going at it.
I try to get to make it a question I know how to answer.
Yeah, no, thank you. Very cool talk.
Okay, thanks Hugo for your question. I appreciate it.
Yeah, thank you.
We welcome more questions. Another generic one from me, Yilin. You've had a very having a very successful postdoctoral career, getting into a junior professorial role in France. If you reflected on your journey in mathematical sciences to date, what advice would you give a younger Yilin as an undergraduate or PhD student?
Oh, okay, advice. Have fun. Yeah, I think it's I guess as a student, I consider that as an advantage, because you're not expected to know a lot, and you can be the most ignorant person in the room, and I enjoy being ignorant and ask a lot of dumb questions. Maybe, I don't know, maybe when one gets older, or if you get very successful in career, then you feel less comfortable asking stupid, dumb questions. And I hope I can still keep doing that and ask all the questions. But definitely don't be afraid. And as long as you can understand and learn something, I guess, yeah. That's an advantage to have, actually.
Okay, excellent. Well, if you have a question, are these beautiful slides available online? The answer to that is yes. Yilin has very kindly allowed us to share her slides following this seminar, which we'll provide on online, and we'll send out an email with the link to those. So thanks, Yilin.
You're welcome. Yeah, with pleasure.
Okay, well, here we have, yep, there's a great, and thanks. That brings us to the end of the questions, Yilin. Thank you very much for your
Thank you for coming.
Sharing your knowledge and insights. We really do appreciate it. So on behalf of everyone that attended today, thank you. We hope to be able to have you visit us in Australia,
Yeah, I hope so.
Matrix and Creswick.